Very good morning and good afternoon. On behalf of IEEE PES Madras chapter, it is a great pleasure to introduce Professor Arindam Ghosh, who is professor at School of Electrical Engineering, Computer and Math Science at Curtin, Australia. I really feel fortunate to have long association of about 24 years with Professor Ghosh since I joined as his Ph.D. student in Department of Electrical Engineering, IIT Kanpur in 1998. Professor Ghosh's achievement and contributions are vast and really cannot be stated in a few minutes. However, I shall make an attempt to give his brief introduction. Professor Ghosh sir received Bachelor of Engineering and Master of Engineering in years 1975 and 1978 from Calcutta University, India. He received his Ph.D. degree in Electrical Engineering from University of Calgary, Canada in 1983. From 1985 to 2006, he was with the Department of Electrical Engineering, IIT Kanpur. And then from 2006 to 2013, he was with the Queensland University of Technology, Brisbane, Australia. And from 2013 till now, he is a professor with the Curtin University, Perth, Western Australia. His current research interests include renewable energy and distributed generations, microgrid systems, power electronic applications in power system. Mr. Ghosh is a fellow of IEEE, fellow of INAE, and he is also a IEEE PES distinguished lecturer. He has about more than 450 publications of very high quality in international journals and conferences. And under his supervision, almost more than 100 higher degree research students have graduated. He is author of 2 books and edited more than 4 books. He has received 20 research projects, more than 20 research projects of about $10 million grant. Now I request Professor Ghosh sir to proceed to deliver his expert talk on microgrid systems. Thank you very much, sir.
Thank you, Mahesh, and thank you, everybody, and good morning, all. The beginning, say thank you for inviting me for this lecture. It's always a pleasure to see Mahesh and others as well. So let me start. What is called a microgrid? All you guys know what microgrid is, because this concept has been there for several years now. It was first proposed by actually Professor Lasseter of the University of Wisconsin, Madison, on behalf of CERS, which is Consortium of Electric Reliability Technology Solutions in California. Since then, it has caught the attention of various people in various all over the world. But if we have to say, it's basically a small power distribution grid where the generations and loads are placed in close proximity. There are various definitions, but all these definitions actually point out these following points. That it incorporates multiple loads, it will incorporate multiple distributed energy resources, is able to island from the utility grid, it can act as a single controllable unity, it operates nominally in grid connected mode, and has clear boundaries. That means you cannot say the whole system is a microgrid. You have to have a clear boundary of what you define as a microgrid. Now, if you see, this is the diagram, which I have drawn, of course. So if you see, you can have the central generation, transmission lines, then substation transformer, and this is called PCC, which is a point of common coupling between the central generation distribution substation and the microgrid. So microgrid can have wind turbines, it can have rooftop PV, it can have house with EV, it can have controllers, it can have battery storage system, diesel, etc., etc. And the controller will look at the markets, it will look at the weather forecast, everything, all these. We will talk about these things a little bit later. Now, if you look at this schematic diagram, you have the central generator, you can have wind farm, you can have solar farm, you have a substation, and you have all these residential houses, smart appliances, PV, battery, distributed generation, wind turbines, fuel cells, all that. And there will be some communication link between all these, which are going to go back to central control. Now, if you look at this microgrid, there has been, we don't have really time to go through this, but microgrid installations are taking place. And you know where they are taking installations? I mean, you have municipalities, like your town people, they are establishing microgrid. Ports, military installations. Military installations is for the simple reason that if something happens and your command and control center, which is located at grid, if it goes down, then you can switch over to microgrid, which people from outside cannot hack. It can have industrial facilities, logistic hubs. That's also very important, like data centers, etc. And then correction facilities, means jails, hospitals, university campuses, etc. So if you look at the microgrid installation, people are putting microgrids, but the reason for putting these microgrids are different for different people. So they are putting the microgrids for different purposes, but the end result is the same, that you are getting mostly renewable based power supply system. And you are, if you want, you can actually switch off from the main grid. Okay. So as I said, they are diverse, and of course, in remote area application, is still one of the most attractive solutions for remote area. And I will also say, now people are talking about microgrid in space. You know, when you want to set up a power supply system in space or in moon or somewhere, they are talking about how to put a microgrid there. It has to be a microgrid, because you cannot take a transmission line from here to, say, the to the moon, or from here to that station, space station, okay, which is few hundred kilometers from the Earth. Okay. The remote area microgrid is another important concept, as I mentioned. Basically, if you look at the renewable sources, I mean, at least in Australia, there are many rooftop PVs, and these rooftop PVs are in homes of people who can afford. Okay, so the major beneficiary are people who are living in urban area. Unfortunately, about 1.2 billion people in this planet still do not have access to electricity, which is a really sad story. And even if you look at that, I mean, say Australia has many remote communities, and these remote communities, their power supply is mostly through diesel. And because it's not possible to take a transmission line to those remote communities, and those communities might have only 500 to 100 people, 50 to 100 people. So it's not possible to take power over there. So what they usually use now is diesel. But the main problem with diesel is not only it's polluting, the other problem is that you have to carry, I mean, I have shown you um, the map of Western Australia. If you carry diesel from here to those remote community, which is 2,000 kilometers north, the cost of the transport itself is again a big problem, big issue. So if you can now have diesel, of course, for backup, but you can have PV and wind, you can, if possible, micro hydro, or if you have biomass gasification, then using all these, you can have a quite pretty decent size remote area microgrid. So let's go over to microgrid components. A microgrid are supplied by distributed generators. I will talk about that or basically if you combine distributed generators with batteries, then they are usually called distributed energy resources. So DGs and DERs, they are more or less same. I mean, some people prefer to call it DG, some people call it DER, but basically it's distributed generators plus battery. Battery is not a generator, it's a resource. A microgrid is connected to the utility grid at one PCC, one single point of communication.
Excuse me, please switch off your microphones.
Microgrid can operate either in grid connected or in islanded mode. And when what we say islanding is that once the microgrid is disconnected from the grid. In the islanded mode, the DGs connected to the microgrid must supply its load. Failing this, load shedding will be required. Of course, all these make sense. I mean, you are in an island, and suppose your microgrid capacity is 500 kilowatt, and your load is 600 kilowatts. Of course, you cannot supply 100 kilowatt extra, so you have to disconnect. Okay. Now, the other thing that is of importance is that microgrid types of generators, like inertial, like diesel or natural gas, which actually power a synchronous generator. Now, a synchronous generator it can store rotating kinetic energy, which is good from the point of view of fault right through, but these are also polluting. Then you can have non-inertial, that is converter interface, like PV, fuel cell, microturbine, battery, etc., etc. Obviously, they don't have inertia because the inverter, you ask it to change a voltage level to another, it will do it immediately. Then dispatchable. Dispatchable means we can actually DR that can be controlled depending on load demand. Like your load is more, you just pump in more diesel, open the throttle. And so they are dispatchable. So dispatchable diesel, natural gas, batteries, fuel cell, microturbine, etc., which do not depend on the weather condition. And the non-dispatchable ones are PV and wind. Now, if you look at it, suppose you have a wind turbine, and your wind turbine is rated, say, at 2 megawatt. But it doesn't matter whether it is rated 2 megawatt or 2 kilowatt. If the prevailing wind is not there, it's not going to be able to produce that much power. So you cannot say that, okay, I have a 2 megawatt wind turbine, so I shall be able to supply a 2 megawatt load. That's not true. So basically what happens is that you draw the maximum power that is available from these turbines or even PV, and they are called maximum power point tracking mode. And in these modes, you try to draw as much power as possible from these sources. Okay, they are called non-dispatchable. And the other problem is that they are intermittent in nature as well. That means, suppose it is bright and sunny outside now, and suddenly a cloud cover comes. So the sun's power will drop drastically. So basically, so that's why they are called intermittent. Similarly, wind can change direction, it can stop blowing, and all that kind happen. Okay, so that's why they are also called intermittent. Now, when you want to plan for something which has got all these things, you have to. The planning actually itself is a massive task. Now, before we do that, to go into the details of microgrid, let me tell you about the converter modes of operation. Okay, there are three modes. I mean, see, these definitions are, what should I say? These definitions are basically somewhat ambiguous. But once I explain them, it will be clear to you what each of these converters do. Okay, one is, say, what is called grid forming. So here, what you do, you supply the voltage magnitude and the frequency to the converter, and the converter will then produce a set of voltages. The star here means the reference, okay? Reference. F star E star means the reference voltage, magnitude, and the frequency. Then it will produce a set of voltages, and then it will put it to AC bus through an impedance. Okay, so that's what is called grid forming. Now, what is it? I mean, if you want to say inject power to the grid, and you say, okay, I don't want to control the power flow, the power flow is not under my control. All I can do is that inject a voltage in the grid frequency with this phase angle. Okay, so that is basically what it is. So basically, this is you can have a remote area microgrid operating like this. You can have a UPS or something like that. So you are doing grid forming, and because these are all in parallel, so you can parallelly connect several such units, provided that the impedance Z is large enough to separate all these units in parallel. Okay, whereas if you look at grid feeding, is what you are doing is you are given a P and Q reference, real and reactive power reference, and from these two references, you are generating a current and you are injecting the current to the AC bus. For example, you are doing a maximum power point tracking in a PV, where the maximum power point tracker uses a DC-DC converter that sets the P reference, and suppose your Q reference is 0, then you take that and you convert it into a current source and you inject it with the grid at the same frequency as of the grid. So here, paralleling them, because you are injecting current, like paralleling these things are much easier than paralleling these, because these have the problem that you have one voltage source. See, suppose it's like this. It's a voltage source here. It's a voltage source here. Now this voltage source is trying to hold a voltage here, and you don't have enough separation for another voltage source to hold the voltage here. So what they will do, they will fight against each other. Whereas here, you are injecting a current, you are injecting another current, you are injecting another current, so there is absolutely no problem. However, this grid feeding that they are feeding to the grid, and this grid feeding converters, they have a problem. They can work in parallel, but if once the grid goes away, they have to switch off. Suppose there is a grid, the grid trips. Where are you going to inject the power? So unless you stop immediately, there will be a collapse here. Okay, so they cannot. They can work parallelly with the grid, but they cannot work without the grid. Here, whereas if you have a load here, you can keep on supplying the load even if your grid goes off. So that is called, these are the two things, grid forming and grid feeding. So this is used for, say, solar PV. This is used for as a UPS or islanded power supply or something. And this is the mode in which all the distributed generators in a grid, in a microgrid operates. Here what you have P, Q, voltage magnitude and frequency. From there, you actually will look at that, you will find the voltage magnitude and frequency, and then you will produce this voltage, and then voltage will go into AC bus. So this is the mode of operation that we are going to look at. Now, if you look at this grid forming, so what you do, you have measure the frequency, you take a integral of it, you get the angle, and then this angle you take it and you put it to DQ converter, and with that DQ converter you convert the angle of the you convert the voltage and the current into two quantities. These you can compare them with your reference voltage, D and Q axis. That is, if you say that, okay, I want to inject, say, 1 kilovolt with a phase angle of 20 degree, then you have three, assuming balance operation, phase A will be 1 kilovolt, 20 degree angle, phase B will be 1 kilovolt minus 100 degree angle, and phase C should be 1 kilovolt plus 140 degree angle. So from there, you convert them into VD and VQ. And once you get these quantities, you put it through a PI controller. That will set the references for your ID and IQ. And then this ID and IQ will come here. You put another PI controller. And then you do DQ to ABC transformation. Then you take these outputs, the U's are the outputs, and you compare them with the triangular carrier waveform, and then you can find the switching. Okay, so that's simple grid forming this thing. I have Mahesh will know, we have a better plan that we can actually doing without doing all this. You can actually take same thing, D and Q axis conversion. You have VD, VQ, ID, IQ, and then you combine them and you design a state feedback controller. Here again, you have all these references. So you have the references, you design a state feedback controller, and the state feedback controller, you can do any linear quadratic control, pole placement control, or whatever. Then you get this D and Q axis, the control variable, you DQ to ABC transformation, and then with this transformation, again, you go through a triangular carrier wave, and then switching pulses. Now, obviously the performance, because this is optimal control base, the performance of this will be much better than that of even if you try to optimize the operations of PI controllers, you will never be able to get this kind of performance. Now, the grid feeding converters, its a simple algorithm is like this. Suppose you have a specified active and reactive power. eh? So, and suppose this is the in alpha beta domain. See, using alpha beta domain has the advantage here. Here you can see that you need the grid frequency to synchronize the operation of all this. Okay. Whereas if you do, sorry, whereas you do in alpha beta domain, then your V alpha and V beta are the alpha beta transformation. And alpha beta transformation, remember, it doesn't have any sine or cosine. It has only factors of half root 3 by 2 and minus root 3 by 2. So there is no, what is it called? No knowledge of the system frequency or angle or anything is required. So this is the advantage of this. So once you write P star and Q star in this form, where V alpha and V beta are based on the measured quantity, and I alpha star, I beta star are the reference current that you want, then from P star, Q star, knowing these quantities, you can find the output currents given by this equation. Once you find the output currents, this and this, you take the inverse transformation to get the current ABC. And then the current ABC, you can actually follow them using anything, I mean, any principle. You can actually have an L filter and try to do a hysteretic current control, or you can have an L filter and try to do output feedback control, or whatever. It doesn't matter. So this is the beauty of this. When you do grid feeding inverter, if you do it in alpha beta domain, you don't need to know too much about the grid. Now, these, as I mentioned, grid supporting converters. These grid supporting converters are used for islanded operation of microgrid. The input to these converters on the DC side are the DGs or DERs, whatever you call them. And these converters are required to produce output voltages depending on active reactive power, voltage magnitude, and frequency. And these DERs are connected to the microgrid to share power according to their rating. So we shall see. All right. So before we go, let's look at this equation. Now, suppose you have this circuit. You have a source here, you have a receiver here, and that is connected through a feeder with impedance, with an impedance with R and X. Now assume that V1 is V angle delta and V2 is V angle 0. Then the active and reactive power you can easily write as this, which is you can find in any undergraduate textbook. Now suppose R is much less than X. Okay, R is very small, so neglect it. So what we will have, this R will become 0, this will become 0, this will become 0, this will become 0. So we will have this relation and these two relations. Okay, so this will be 0, this will be 0. So we call it inductive grid. That the grid is predominantly inductive. So when R is much smaller than X. Also, if we assume delta to be equal to 0, like this is V1, V2 over X, sine delta. Now, if delta is equal to 0, then sine delta is equal to delta. And also cos delta will be equal to 1. Okay. So if we do that, we can actually rewrite those two equations like this. P1 is B1 B2 over X delta, because sine delta is equal to delta. So delta becomes proportional to P. And Q1, from this relation, you see V1 V2 is proportional to Q. So basically what we have is that delta is proportional to frequency difference, and voltage difference is proportional to P. Now again, d delta dt is actually nothing but frequency. So what we can say, delta is somewhat related to frequency. So from that, we get what is power versus frequency and reactive power versus voltage magnitude Droop equation. So this is given by this. I suppose the microgrid has n generators, total number of n generators. So the frequency of each individual generator will be f star. F star is the rated frequency. And the rated frequency is what? It's 50 hertz. Okay. Then N1, half of your rated power minus your power. Similarly, Vi is V star, which is 1 per unit voltage, rated voltage, whatever. M1 is half your reactive power minus reactive power for each individual unit, where N and M are called the Droop gates. So if you look at this here, the frequency is like this, frequency versus power. So if you look at this here, then this is the point where if this is your DG2, this is its half rated power. So when the frequency is 50 hertz, it is supplying half rated power. When the frequency is 50 hertz for P1, it is supplying its half rated power. So this is the Droop characteristic. And for the voltage, when it is supplying its rated, this should be Q2 by 2, right? When it is supplying its rated voltage, the power should be Q2 by 2. Okay, so that's it. So there is a bit this thing here. So anyway, so let's look at a simple calculation. Suppose you have two DGs with ratings of 200 kilowatt and 50 kilowatt. So you can see DG1 is rated 200 kilowatt, DG2 is rated 50 kilowatt. So this is 4 times the size of this one. So that means if I have, say, a load, then if I divide that load by 5, okay, then this one will supply 4/5 of that load, and this one will supply 1/5 of the load. Suppose the total load is 250 kilowatt, then this supplies 200 kilowatt, this supplies 50 kilowatt. If the load is just half of it, 125 kilowatt, then it should supply 100 kilowatt, this should supply 25 kilowatt, so that their proportion is 4:1. Okay. Now, suppose I say I maintain the frequency deviation to plus minus 0.5 hertz. That means I don't want to let the frequency go above 50.5 hertz and fall below 49.5 hertz. That 0.5 hertz is just a number. It can be 1 hertz too. It doesn't make any difference. Depends on the kind of load that you have. If your load is not able to, like adjustable speed drives or something, if it is not able to do much frequency deviation, tolerate much frequency deviation, then it is better to restrict the frequency variation within a specified limit. Most other household appliances, they don't care if your frequency is 49 hertz or 51 hertz, but some of them might. So I just say, okay, let's restrict to 0.5 hertz. Okay. So now if I put this in this equation here, so what I see is that, look at it this way. When this one, look at one of the DGs. When it is supplying its maximum rated power, so what will be the frequency here? Frequency will be, see, here it will be at the bottom. So the frequency will be F min, which is 49.5 hertz. So the difference of F1 minus F star will be 0.5 hertz. So then what you have is N times half of your rated power is equal to minus 0.5 hertz. N times minus half of your, because if suppose this is the total rating is 1 megawatt, you are supplying 1 megawatt, and then it will be 500 kilowatt. So the difference is minus 500 kilowatt. So minus 0.5 is N times minus 500 kilowatt. Okay. So if you look at that equation for these two DGs, then what we get is minus 0.5 hertz, N1 for DG1, 0.1 because it's 200 kilowatt, half of it is 100 kilowatt, which is in megawatt is 0.1 megawatt. Its maximum is 0.2 megawatt. So this is equal to minus 0.1 megawatt. So this results in 5 hertz per megawatt. Remember, you have to define this unit properly. So if you choose it as 200 and 100 here, then it will be 0.5 into 10 to the power minus 3 hertz per kilowatt. So that's important. So, and the other thing that you can also do the same thing in the same way, and you can find N2, which is this one, 50 kilowatt, will be 20 hertz per megawatt. So for each megawatt change, the frequency will change by 20 hertz. In fact, if you follow the same procedure, the Droop gain then you will be selecting is P1 times N1 equal to P2 times N2 up to Pn star N1 into alpha. There will be a constant. In fact, if you look at this, this is 5 times 0.2 is equal to 1 hertz, and 20 times 0.05 is also 1 hertz. Okay, so something like that. So this is the Droop gain selection. Now, if we look at this, the power supplied by these two, just one inductive grid performance, then you can see that these two powers are actually quite matching, because this is 4 times that of that one. And this is just, I think I remember about 140, and this is 37.5 or something. So they are very closely matching. And as a result of which, your frequency is also matching. After the initial transients, the frequency of these two overlap. And in fact, what is interesting is that if we use these equations, using that 0.5 hertz deviation, I can predict, depending on what will be the power here, I can predict what will be the operating frequency, because everything is known. I know this, this is 0.1 megahertz, and you can see if it is say 0.15 megawatt, so the difference is 0.05 times N1, and you subtract it from the frequency, you will get a point somewhere here, okay, below. And you see, when the frequency is, when the supplied power, this quantity is positive, I mean, this quantity is positive, that means you are supplying less than the half rated power, your frequency will be above 50 hertz. So it's very easy to determine that using this calculation that I showed. You say if your steady state power output is this much, you can calculate what will be your frequency. Okay. So that's why, I mean, if you compute using these two, you will see the frequency is same. The only problem here is your reactive power sharing doesn't match. That's the problem. Okay. So your reactive power sharing will not match. That is usually, you say, okay, how do I care? I mean, I'm more or less interested in only active power. So why the hell should I care about reactive power? There is a problem here. See, if you have an inverter, the inverter will have a current rating. Okay, the current rating is what is it? Is your under root of P square plus Q square divided by voltage. So if you have a small rated inverter, your voltage magnitude is constant or supposed to be constant throughout the network, not much variation. So if you have a smaller inverter and you are supplying a very large amount of reactive power, then what happens is that if your reactive power droop is not that good, okay, the smaller inverter might end up supplying more reactive power, will result in heating and all that. So that's also not very desirable. So a lot of people use, with the reactive power, they use a proportional plus integral controller to bring the voltage or the reactive power in such a way that the whatever the reactive power is required is available. But those are all second degree improvements that you can do. Okay, several things that can be done. Now suppose I have a resistive resistive grid. So what does that mean? That resistive grid is that means your usually if you look at power transmission system, the grids are inductive because modern power transmission, high voltage transmission systems, the resistance is almost negligible. So the grids are inductive. So when the grids are inductive, what you do is that you can neglect the resistance. But for power distribution systems, in fact, resistances are quite high, so much so that you can actually neglect the inductance or reactance. Sometimes they might be 1 to 1 or something like that. So basically, you cannot assume the grids are inductive. So now if we go back to those equations and neglect the x, previously we neglected the r, now we neglect the x. So what you get is this equation. So you can see now the voltage difference is dependent on P and the angle is dependent on Q. Okay, so voltage difference is dependent on P and angle is dependent on Q. So that gives you Vp and Qf Droop equation, which is the same as before. So only thing is that I have interchanged Q with P here. Okay, so this is frequency versus this thing, Q, and this is voltage versus P. And you can see that this slope is negative. The slope, here the slope is this way, there the slope is this way. So this is whatever, a positive slope, and this slope is negative because of the sign here. Okay, negative sign here. Okay, so that's the. Now, if you look at this performance here, you will see the reactive power is shared in the ratio of 4:1. As a result of which your frequency is now converged of the two DGs. But the main problem here is your real power is not shared properly. Now you say, oh, that's not good. Obviously, my generators should share power according to their ratings. Now, if I am not able to do that, so what good is it? Obviously, we have to modify this method. Or modify. We have to do alternate solutions for this. Okay. So previously, what we said is that when we inductive line, everything is good. You select frequency versus P and Q versus B. Now the power sharing is very accurate, as a result of which frequency match. When you have a resistive grid, your reactive power sharing is accurate, but your real power sharing is not good. So you will say, okay, I want the real power sharing to be more accurate. I can have little bit inaccuracy in reactive power, but not in real power. So what do we do? So there's one group of people. They said, okay, what I can do is that I will do a transformation of this. Suppose the impedance is given by this and this. That is R plus X. So mod Z angle theta. So mod Z obviously is R square over X square, square root, and theta is the angle between these two. So they say, okay, we'll make a transformation matrix, which is given by, we'll define a new variable, P prime, Q prime, which is transformation matrix multiplied by P and Q, and the transformation matrix is given by this equation, so which is mod X by mod Z minus R by Z and so on and so forth. So what it says is that, see, when the R by X equal to 0, that means the line is mostly inductive, P primes become P and Q prime become Q, which makes sense. Whereas when the line is heavily resistive, that is X equal to 0, and this becomes infinity, so your theta will become 0. So here again we get the same relation, your Q prime becomes P and your P primes become minus Q, which is same as we have seen earlier, just the last one. However, in between, this will be like this. So if your R by X is equal to 1, then theta is equal to 45 degree, then it will be like this, okay? So it will be a mixture of P and Q. This will also be a mixture of P and Q, which makes sense actually. So basically, your lines are neither this nor this. So what we have to do is somewhere, it can be somewhere here or anywhere between this and this. That R by X could be 1, could be 2, could be 10 or whatever. Or it could be even less than 1. Okay. So if you do that, so what we do is now instead of doing Droop sharing using P and Q, we'll do by P prime and Q prime. So if we do by this, so what we do is that F minus F prime is N P prime star minus P prime. And this is V Q prime star minus Q prime. So it's given by this relation. So that transformation matrix relation. So if you plug it in those relations, you can easily get these equations from this one. Okay, the relation between P and Q are given by this. So the main problem is with this is a very nice method. The main problem with this is that how do you find the line parameters? Okay, all right. Now, before I do that, let me show you my result. You can see here the results are perfect. Okay, the frequencies match, the power and reactive power, they both share according to that ratio 4:1. They're beautiful results, sir. Okay, quite wonderful. Because I know, what this is. Exactly, I know. For both these DGs, to the load point, I know the line resistance and reactance. So if I know, it's very good. If I don't know, then I am what? And suppose what happens is that you have a system where you have got several DGs and loads. So between say 1 DG and say DG1, between DG1 and DG2, there are two loads. Okay, and these in between the loads, the Thevenin impedance will change if the load changes, or the Thevenin impedance between a DG and another a load will change if one of the DGs go out of service. So basically, the main problem with this is that there is no way of knowing what the impedance is. So you have to use some kind of algorithm or the estimation of impedance, which is really a nuisance. But this is very elegant method, provided you know the impedances accurately. Maybe Mahesh will give this problem to one of his students to tackle. Okay. So, or any of you can tackle this problem. It's a very nice problem as itself. However, there are simple methods which are called virtual impedance. So what happens is, it's like this, okay? Suppose you are using a Droop equation, whatever the other two, either PF, QV, or QF, PV. So you have those equations. Suppose let's talk about this. Suppose you have a highly resistive line. Suppose you have a highly resistive line. So you said, oh, I want to make the line inductive. So what I will do, I will put a very big inductor. I will put a very big output inductor in front of my output of my converter. Okay, so much so that it will actually be much larger than the resistance in the circuit. People will say, okay, but that's stupid because the inductor will cause power factor problem, it will cause voltage drop, etc., etc. Similarly, if you have a highly inductive line, you will say, I will put a resistor, but the resistor will cause voltage drop. Okay, so neither of these are feasible solution. But then some researchers, mainly Guerrero and his team, they said, okay, we don't do all that. We don't have to do put a physical impedance there. All we can do is we can put a virtual impedance. What is the virtual impedance? So what you see here is this, you have got this voltage from the Droop equation. Now you say, okay, I measure the current output of the inverter and subtract that current through a virtual impedance such that what happens is I get a new set of voltages. So what you have is your voltage reference here, which you have calculated, and you put a virtual impedance here. And then if your line is resistive, then if I subtract resistance, the virtual impedance, if it is a resistance, then what I am going to do is I am going to reduce that resistance by putting a resistance here. Whereas if my line is inductive, I put an inductance here. So I take a ddt of I and I subtract it from here. Okay. Z means L di dt. So I put a differentiator. I put the current through a differentiator and put it through this and subtract it from the voltage. So I will negate the effect of impedance, inductance, or if it is a resistive line, I will negate the influence of the resistance. So this is the basic virtual impedance concept. It's very simple. So if you see virtual resistance, you can see that the real power sharing, this is a resistive line. And if you do that, the real power sharing is pretty accurate. Reactive power is still not that good, but it's okay. But I am putting a PF and QB Droop, which is what we have discussed, and put a virtual resistance. So the results are pretty good. And this is QF and PB Droop. And virtual, this is not resistance, actually, virtual impedance or reactance or inductance. Okay, so this is wrong. Okay, so anyway, so this is again, you can see the frequencies match, reactive power is accurate, and real power is also accurate. Okay, so that's the beauty of this situation. Okay, so you can do both. To improve your real and reactive power sharing, you can put the virtual resistance or virtual impedance is good. Okay, now these are called the primary controllers of these DGs in a microgrid. Now remember, what we talked about we are talking about actually converter interface, but there is no hard and fast rule. In fact, you can even use a diesel generator here. In fact, one of my students, she worked with a combination of a diesel generator and a converter interface or several converter interface. So all you have to do for diesel generator, you have to take the W omega and you give it to your IC engine, and you take the voltage magnitude, give it to our voltage regulator of a synchronous generator. So basically, even though with this, we are talking about, as if we are talking about converters, but you can take the same information, give it to a diesel generator or any other thing like that. You can even have a controller for PV, you can have a controller for wind turbine, etc., etc., etc. Now, if you look at this control hierarchy of a microgrid, now there are 3 levels, okay? So let's look at this diagram here. So the levels are, this is microgrid and microgrid load, etc., etc. There are several of them. So the primary controller are essentially the Droop controller. We will talk about that in second. So these are then you have secondary controllers, which are sitting inside the microgrid itself. So these are the primary controller, these are the secondary controllers, and the secondary controllers are talking to the primary control. And then there is something called a tertiary controller. The tertiary controller is talking to the secondary controller. Okay, so this is the 3 hierarchies. Now let's look at what are the controllers. Okay, primary controller is the Droop control, as I mentioned. Remember, Droop control is a steady state concept. As I mentioned, it's a steady state concept in the sense that once your system attains steady state, then you will have this voltage, this power, and this frequency. However, if you have very fast load change, very fast load change, then the Droop controller will not be able to, it might cause system instability, okay? So what you have to do is, you have to then rely on the secondary controller to do correction so that your system doesn't become unstable. Now there are non-Droop based control method that includes a centralized controller. Now, for example, if I have IIT Madras as my, I am setting up a microgrid in IIT Chennai, IIT Madras. What's the area? Not very big. Okay. So I can have underground broadband cable everywhere. I have load centers, I can measure their values, voltage, angle, because these days it's very easy. Just put a microprocessor, all you need is a synchronizing signal, and I can do the measurements based on the synchronizing signal, and I can have a phasor measurement unit. So I can measure the voltage and angle and current and angle and all that in every bus. And I say, okay, this is my load, and I do a very fast load flow, and I can schedule all my generators so that that load flow, and I know the apparent impedance of the lines, etc. So, and I can actually do a centralized control without any problem at all. But requirements is small geographical area and very high speed network, which is, as I said, if it is a small geographical area, high speed network is possible. All right. Now, the thing is, what's the problem? That you have a single point of failure, the communication network has broken somewhere, then the DGs don't know what to do, and there will be a total catastrophe. The other one is called master safe controller. Then one DG will act like a master and hold the network voltage, and the other will supply the load. It's sort of like a concept of load flow. That one generator sets the angle and the others will supply the load. So it's also same. I mean, it's a little bit more refined, but this also will require communication network. So even though these methods are implementable, but they are not, because the Droop control method is only relies on local measurement. So they are actually that way more reliable. And you add the secondary controller with that. Okay. So secondary controller is basically energy management, microgrid energy management. It can be centralized or decentralized here also. So the centralized control includes a microgrid central controller. So you still have the central controller concept, but it is not affecting the primary control. Its only thing is that when there is a very fast load change or something like that, what is happening, what you do is that you try to do a secondary level improvement on the signal of voltage and frequency signal. So what you do is that you thereby negate the influence of these fast changes. So it sends commands to the primary controller of each DR to compensate for the deviation of their output voltage and frequency from their respective set points. Okay, so that's the secondary controller. Now, that's a centralized. Again, you can have a decentralized controller. In that, each secondary controller can produce appropriate control correction for the primary controllers and by considering the measurement from other units. So let's look at this, what is that distributed or decentralized. What you have is that each primary controller has its agent. This one has its agent. And these agents are talking to each other. Okay? And they are talking to each other and the agents are sending signal to microgrid central controller. So rather than this one telling these guys what to do, now the agents are deciding amongst themselves what to do. Okay? And then communicating with the microgrid central controller. So the whole thing is distributed. So it has got this agent is passing this information to central controller, and the central controller is passing the information to these agents as well. Okay. Then tertiary control. Now this is the slowest level. Okay. Slowest level is slowest level. It's sitting on top. And this level, actually, some people say you shouldn't consider this as a microgrid controller because this is part of the main grid operation. Okay. So it controls the power exchange between the microgrids and between the microgrid and the main grid. So if two microgrids are trying to exchange power, then the tertiary controller will come, or if any of the microgrids or number of microgrids are trying to communicate or exchange power with the main grid, then it will be under the purview of tertiary control. So some of the objectives are microgrid overload relieving, reliability improvement, resilience improvement, loss minimization, etc., etc., etc. So even the markets, etc., they will come in this tertiary level. Now people are talking about resilience improvement using microgrid. Okay, we'll talk about that in this. So coupled microgrid. Now we are talking about smart distribution. All right. Now the smart distribution, what is it? What is a smart distribution? These days, everything is smart. Only we people are dumb. Okay, but actually, with the improvement in the communication technology, with the computer speed going up, with artificial intelligence coming up, or machine learning as they call it, a lot of things are going to happen. The things that we see will change very rapidly. So our smart distribution system will have improved reliability. That means if there is some fault, faults are going to happen. Faults will happen. You cannot stop it. But the impact of the faults should be less. So the network should be able to self-heal, that if you have a fault here, then the network should determine that, okay, the fault is between point A and B, so I should try to channelize power through an alternate route. Now we can have fuel diversity, and you can have generation efficiency through combined heat and power. Remember, combined heat and power is not a very big deal in either India or Australia. But when we talk about, say, a place like Canada, for example, you have a fuel cell or you have a microturbine. The gas that you are coming out of the turbine, you use it in the pipe of a building where thereby you heat the building. So that kind of things. There are several advantages in forming distribution systems that with network of microgrids. And the network of microgrid can improve the resilience of power system. How? That a microgrid can island itself in case of extreme event. Suppose there is an earthquake or tsunami or something like that. So the part of the network has gone down. All right. So the microgrid, in fact, this has happened in the Great Japan Tsunami of 2011. There was one microgrid which was in a place called near Fukushima, where the reactor accident occurred. A place called Sendai, and it was a university campus microgrid that kept on operating for 2.5 to 3 days, even when everything else was totally devastated. So the microgrid can island itself in case of an extreme event. Okay, it can keep on supplying its local demand through a much lesser impact of the grid failure. Then microgrid, while interacting with a utility grid, can provide ancillary support like voltage support and black start support. Suppose the whole thing has gone down, you want to restart it, the reference point will be the microgrid, and the rest of the grid will synchronize with the grid. However, there are many issues there, many issues. Okay, like energy trading. I want to do, if I have set up a microgrid, my main aim is to supply my local customers, but I want to make some money as well. So how do I do energy trading? So you have to do energy trading. For that, you need multi-objective optimization for peak shaving or loss minimization, comprehensive energy management, etc. All these have to take into account for the proper functioning of coupled microgrid. Now let us look at some of the structures of a coupled microgrid. It says serial microgrid on a single feeder. So you have the main grid like this, and there is one bus. So you have two microgrids connected to it. So you have SW1, which is connecting this microgrid to this bus, and SW2, which is connecting this microgrid to microgrid 1. So there are, these two will be grid connected when obviously this switch is closed and this switch is closed. So this will be, microgrid 1 will be grid connected, and microgrid 2 will be islanded when this switch is closed and this switch is open. And once this gets islanded, it doesn't matter if this switch is open, this microgrid will islanded, but this microgrid can operate with conjunction with microgrid 2 if this switch is closed. But if this switch is open, then both microgrids are islanded. Then similarly, you have parallel microgrids on a single feeder. What you have is you have a main grid, the feeder going there. You have one switch 1, one switch 2, and have intermittent switch here as well. Okay. So depending on this, I mean, for example, if this switch is open, these two switches are closed. They are grid connected, both the microgrids. Suppose this switch is open, this is open, and this is open, then both microgrids are islanded. Similarly, this switch is closed, these two are open, then these two are acting together. So all these 8, because there are 3 switches, there will be 2 to the power 3, that is 8 combinations, which are given in this table. And then you can have microgrids in multiple feeders. That is, you have one microgrid, two microgrid, and they're connected between feeders. And there are various possible combinations here as well. So what is a smart distribution? Smart distribution can be achieved through the fast control of hundreds of individual DER units. This will require real-time information on each DER unit and loads. Suppose you have the traditional system, central generation, transmission, substation, distribution network, and then you have a microgrid, all of them. But these microgrids are actually talking, only transferring power through this is called power exchange highway. So the power exchange between the microgrid or the central generator or microgrids itself will go through this highway. And this isolator can be, if this is an AC system, this isolator can be a back-to-back converter. And once we have the back-to-back converter, the advantage of this, that this microgrid can work independently of this can work independently of this. So all these microgrids will work independently. Only thing is that when they want to exchange power, this will go through this converter. So that is what we are saying. That is the these power isolators here, which isolates this microgrid from the exchange highway. They're basically back-to-back converters. Okay, all right. Now, each microgrid will have plug-and-play DGs that will be nominally expected to supply its local load demand. However, suppose what we do is that suppose this microgrid, all these are working independently and they are supplying their local load demand. Suddenly, this microgrid has a power shortfall. And how to measure the power shortfall? You can use this Droop equation to measure the frequency. And if you see that your frequency is falling below 49.5 hertz, then you know you have a power shortfall. And then you can start drawing that power through your isolator from either of these microgrids or from the AC system. It doesn't make any difference. Okay, so this is basically. Now, the couple of last slides. So what happens is that microgrid cluster, you can have, this is utility grid, this is microgrid, these are all back-to-back converters. You can have three-phase AC here, or even single-phase AC here, but three-phase is more feasible. So, or you can have a DC. Who stops you from having a DC? It's much cheaper, okay? And you will need just one converter, not a back-to-back. And so one converter, the losses will be less. And here your power exchange highway is DC, so the losses will be less. And then your utility grid, you are also connecting it through a AC-DC converter. Now we have done some work on this, and you can find a paper which tells you how to how this DC power exchange highway work. Okay, now the microgrid development is gaining momentum in various parts of the world, especially in Asia and North America. In fact, if you look at the development, really Asia is obviously because of India and China, they are doing a lot of developments. And North America also, because they are the one who started all this. Europe has a little bit different because Europe has massive wind, okay, massive. And in some places they have very huge solar resource, okay. Because they are already quite rich in renewable energy, their development is little lagging. But what we need are places like Africa or South America and so on, or to have a cleaner planet. Okay. And as I said, remote areas, I mean, like there are lots of places in India, Australia, China, and other places where very remote and difficult terrains, and obviously in Africa. So this concept is very attractive in remote areas. And the thing is that in most of these places, there is abundance of sunlight and lots of wind. Mhm. In urban load centers, increasing number of PVs are getting connected. So time will so happen is that people will say, okay, I have so much wind here, so much PV here. I don't want any utility connection. So basically, some people, there is already one concept which is making rounds, which is called VPP, virtual power plant. You know, so the VPP is nothing but a software. Okay, they say, okay, I will do a point-to-point energy trading. They go, suppose they will find 10,000 customers who have got PVs and batteries in their home. They'll say, I will run my software on your system, and then what I will do is that I will do energy trading. You will don't have to do anything. My software will monitor everything, and at the end of the month or maybe quarterly, you will get some profit. Okay, so that is called BPP. But BPP is it's not engineering; it's just a computer science problem. So I don't see it's not an engineering solution. Okay, you don't gain anything other than making some money from this. But I don't like anything which is not engineering solution. Anyway, so the coupled microgrids or microgrid clusters will be developed in pretty soon, and it's going to happen because, as I said, that as people are going to have more and more renewable energy in their mix, they will tell the utility, "Oh, I don't need you." Okay, so poles and wires will go down the drain, except for that bigger loads, like you have a steel plant or something which requires 200 megawatt of power, that will come through bigger system, maybe not coal-fired, but say wind, big wind farms, big solar farms, etc., or hydro. So you can see that there is a lot of scope for doing work in this area, and so a lot of things are still unknown. Anyway, so that's it. Thank you. Any questions?
Thank you very much, sir, for this very classical lecture on microgrids. We really enjoyed thoroughly, and I was noting many things. I was taking notes from your presentation. Again, I become another student once more. So it's covering very wide spectrum, starting from the Droop characteristic to the tertiary stage, and how they are related from one to another. So I really got very delighted at how the connecting dots were in your lectures present.
Thank you, one and all. On behalf of IEEE Power and Energy Society, Madras chapter, I thank resource person Professor Arindam Ghosh, Professor Curtin University, Australia, for his excellent webinar on microgrid systems. The topic is currently a very important one, relevant to power and energy systems. I thank him for accepting our request in spite of his busy schedule. I thank all the participants for attending this very important webinar on microgrid systems. I also thank IEEE Madras chapter for their constant support and encouragement. I also thank the organizers, Dr. Mahesh Kumar, Dr. Sarathi, Dr. Venkatesh Kumar, Dr. M.T. Selvan, Dr. Alagar Murugan, and Dr. K. Palnisamy. Our sincere thanks to IEEE chapters of various institutions supporting this kind of technical activity. Thank you, one and all.
Thank you.